Concept 8. Rolling on an inclined plane. In case of pure rolling on a horizontal surface, the static friction is 0. However, when rolling up or down an inclination, static friction is the only agency that provides torque for rolling. And for both cases of rolling up or down an inclination, the friction force always acts upwards. For rolling, minimum static friction must be available, which can be related to the inclination of the plane. As the inclination of the plane increases, the tendency to slide also increases. Here, we consider the instantaneous equilibrium of the system. This contains the inertial or pseudo forces as we treat the situation as static for better comprehension. Consider a cylinder rolling down an inclined plane. Let us now write the Freebody diagram for the cylinder. The weight of the cylinder acts vertically downwards, which is resolved perpendicular to the inclined plane as mg cos theta and parallel to it as mg sin theta. The cylinder sees a normal force from the inclined plane. Since the cylinder is accelerating downwards, it sees an inertia in the opposite direction. The friction force acts up the inclined plane and is given by mu n, where n is equal to mg cos theta. Find the minimum friction coefficient required to prevent the cylinder from sliding. A rolling member has both linear and angular degrees of freedom. We know that from Newton's second law, T is equal to I alpha, where T is the torque, I is the mass moment of inertia, and alpha is the angular acceleration. Since friction provides angular inertia, we have mu mg cos theta into r is equal to I alpha. We know that alpha in terms of linear acceleration can be written as A by r. Therefore, the expression for torque can be rewritten as I into A by r. Let's number this equation as 2. Simplifying equation 2, we get mu mg cos theta into r square equals Ia, or A is equal to mu mg cos theta into r square by I. Let's number this equation as 3. Acceleration can be found by balancing the horizontal forces. Therefore, ma plus mu mg cos theta is equal to mg sin theta, or A is equal to g sin theta minus mu g cos theta. Substituting the value of A in equation 3, we get the following. Simplifying this, we get the following expression. And further simplifying, we get the following. Let's number this equation as 4. Simplifying equation 4, we get minimum static coefficient of friction required to prevent the cylinder from sliding, or mu is equal to tan theta divided by mr square by I plus 1. It is to be noted that the friction provides angular inertia for the cylinder. Therefore, the friction torque must be greater than or equal to I alpha. Therefore, the condition for perfect rolling and condition for sliding are as shown. In this expression, substituting the value for mr square by I to be 2, we have tan theta divided by 2 plus 1, and simplifying, we get tan theta by 3.